Here we're learning about differential equations. Now, these are probably the most important type of equations in mathematics, and essentially they're just like normal equations, but they've usually got dydx's in them, like derivatives and stuff. We already know how to solve a few differential equations, it's just we haven't called them differential equations yet. And then we'll see some more tricky differential equations. So you'd hopefully be pretty comfortable solving an equation like that for y, and we'll do an example pretty shortly. But then it might be a bit trickier to solve one that has y on the right-hand side as well. And you can have all sorts of funky differential equations, and we'll learn how to solve a whole bunch in this topic. But I want to give you one really famous example of a differential equation, and this is called the Navier-Stokes equations. And pretty much what it defines is when you have like fluids flowing around, like let's say a river, it sort of defines how they move, and they're very well understood when the river is nice. But as soon as you hit like a rock in your river and you've got all this like crazy turbulence happening around there, or like if you're in an airplane and you've got turbulence happening, like what the heck's going on in here? So the Navier-Stokes equations explain pretty much all of this fluid. They explain that and they explain that, but this has a big question mark around it. And the reason is this differential equation, the Navier-Stokes equation, is incredibly hard to solve. In fact, nobody's ever done it, and there's $1 million bounty on it. If you solve the Navier-Stokes equations, which is just a differential equation, you will get $1 million. It's called one of the Millennium Prize problems. There were 7 of those problems posed at the start of the millennium. A couple of them have been solved so far. Navier-Stokes is one of them, and it hasn't been solved, but you do get $1 million if you do it. So have a go if you've got some free time. Anyway, we'll solve some differential equations here. So the first one here is dy dx equals x squared. And essentially to get y, well, it's just going to be the integral of x squared. Now let's do that formally. So dy dx equals x squared. We are going to integrate both sides with respect to x. So what are we left with? Well, we get dy dx on the left-hand side, and then we get x squared dx on the right-hand side. And then sort of like they cancel, so you get y equals the integral of x squared, which is x cubed over 3 plus c. This is called solving by direct integration, and this is what I mean by we already know how to solve a bunch of differential equations. If it's dy dx equals stuff that involves x on the right-hand side, this is just like literally an integration problem. What gets messier is if we have something like dy dx equals y, which is a little bit weird. Now we will learn how to solve this formally, but what we're doing in this topic is we're just verifying that this is a solution. So let's check. Y equals e to the x. Therefore, dy dx, if we differentiate that, also equals e to the x. So if we take this differential equation and we call this bit the left-hand side and we call this bit the right-hand side, then hopefully they should match. So left-hand side is dy dx, which we just agreed is e to the x. And on the right-hand side, that's just y, which is e to the x. So left-hand side does equal the right-hand side. Therefore, y equals e to the x is a solution to the dE. If you're wondering what dE stands for, it's differential equation. Great. Now that's not the only solution. It turns out that y equals 2e to the x also works, because dy dx also equals 2e to the x, so it is the same. So you can think of what all the solutions would look like to this, and all the solutions might look like y equals any number out the front times e to the x. So this is a bit like how we have our plus c on the end. A is just any real number, but it's not plus c, it's times by a constant, which is a little bit weird if we're used to integrals. Anyway, I want to show you a picture of this. So the differential equation says dy by dx equals y, and essentially what that means is that if y equals 1, then our slope should be 1. So sort of same rise, same run. And you can sort of imagine the function continuing up there until it hits 2. But if y is 2, then the slope needs to be 2, so it needs to be a lot steeper, just like that. And it continues up and up and up and up. But then if y equals, by this point it would be hitting y equals 5-ish, and the slope would be 5, so it would be getting crazy steep. And our function sort of looks like this. So if I take any y value like 5, the slope there is 5. If I take a y value like 2, the slope is 2. And a y value like 1, the slope is 1. You can see this function is getting crazy steep, and so this sort of looks like the function y equals e to the x. And that's how this is working with the differential equation. So that is the slope should equal the height at any point. And this is a perfectly good definition of e to the x. The definition is it's the function whose slope equals its height at any point. Anyway, we'll do one more. So we got this. Verify that y equals e to the x squared is the solution to the differential equation. So let's look at dy dx. We're going to need to use the chain rule. So we get e to the x squared times the baby. And then that can be our left-hand side of the differential equation already. If we look at our right-hand side, which is 2xy, and we know that y is e to the x squared. So this gives us 2x e to the x squared. And oh my goodness, they match. Who would have thought? So therefore, y equals e to the x squared is a solution. Now, one more question that I want to do, just because it'll be a bit of fun. Secret question 4. We want to think about the differential equation where the second derivative equals minus of the original function. If you're interested, pause the video and see if you can find a function that when you differentiate it twice, you get minus what you started with. And it turns out that function is sine of x. So let's have a think about this. Dy dx is cos of x. And then d squared y over dx squared, we get minus sine of x, which is minus what we started with, minus y. So that's sort of how differential equations work when there's y involved. And you can get some real funky ones like, I don't know, d squared y over dx squared plus dy dx equals y squared plus 2x cubed plus 1, or something stupid like that. And this would be hard to solve. Like, I wouldn't even know how to solve it. It's probably like impossible to do by hand. I don't know. But you can get funky stuff like that, and it's really awful. But we'll be dealing with some predictable differential equations, but just in this topic, your goal is to verify whether or not something is a solution or not.